All right, we'll take it out of
We gotta take more water.
All right, today we get to two important types of problems, explosions and collisions, which as you'll see, as physical processes, are actually quite similar to each other. Okay, for both of these topics, however, what we have to do first is a specific conservation equation. Now here's how we go about doing this. First of all, we're going to assume that both of these processes will take place on horizontal frictionless surfaces. So what that then means is that the sum of the external forces is equal to zero acting upon the system. Now the system is going to consist of particles exploding apart or particles undergoing some sort of a collision. If it all takes place on a horizontal frictionless surface, then the sum of the external forces is equal to zero. Normal force cancels out with the force of gravity, and there's no friction horizontally. We're going to assume the sum of the external forces is equal to zero. Now I know it was last week, but what that then means is that this quantity, the momentum of the center of mass of the system of particles colliding, system of particles exploding apart, which is equal to the sum of the momenta of the individual objects. This quantity here is equal to a constant. Now remember that momentum, this new quantity, the total amount of motion associated with a system, is mass multiplied by velocity. So think of this, for simplicity, as basically just the velocity of the center of mass. If the sum of the external forces acting on the system is equal to zero, the velocity of the center of mass is equal to a constant. In other words, the momentum of the system is a conserved quantity. So then therefore, if we looked at the change in this quantity, from before the collision to after the collision, or from before the explosion to after the explosion, the change in this quantity is equal to zero, allowing us to come up with a conservation equation. So from before to after the situation, whether it be an explosion or a collision, a change in the momentum of the center of mass, which is equal to the change in the momentum of the individual particles themselves, the left-hand side of the expression here is equal to zero. So what we end up with is a conservation equation. That is, we look to see what happens with the change in the momentum of each of the individual particles from before to after the explosion or the collision, add it all together, and then set it equal to zero. The beauty of this expression is that number one, it's actually really easy to use, and number two, you don't even really have to worry about the center of mass itself. The change in the momentum of the center of mass being equal to zero means that mathematically all that we have to do is we have to take a look at the individual pieces. And then what we do is apply this conservation equation to situations involving explosions and collisions. We'll begin by taking a look at explosions. There's really only two situations that we have to look at. What is called the one-dimensional explosion, and then secondly, the two-dimensional explosion. Diego, you have a question?
Why did you make it of,
Okay, so now, if this quantity is a constant, it's the same number before the explosion as it is after the explosion, it's the same number before the collision as it is after the collision, then the change in that quantity is equal to zero from before to after the process, okay? All right, let's take a look at our two problems for explosions. We'll begin with what is called the one-dimensional explosion. Big seagull. Now I'll demonstrate this here on my desk using some carts. We have a couple of numerical examples to take a look at here in this problem, that is parts A and B. And then lastly in part C, a question about the basic physics of the situation. All this can be easily demonstrated here by using my carts. You'll also find that this is actually quite intuitive, what has to happen in these situations. As I said, the answers here, at least for part A initially, are quite intuitive. Let's set it up in the following way. I have two carts here which are of about the same mass. And let's assume that the surface here underneath is horizontal and frictionless. So the sum of the external forces is equal to 0. And then I cram these guys together, and when I do, I give them some form of elastic potential energy by means of these bands, and then as they explode apart, that potential energy is transformed into the kinetic energy of the carts. Now we're given that after the explosion, this cart here moves off to your right-hand side with a speed of 1 meter per second. Assuming the carts are of equal mass then, what do you suppose the speed of the second cart is going to be in the opposite direction? It's also going to be 1 meter per second. That's intuitively obvious, and that is of course exactly what happens. Okay, showing this eventually in part A of the problem is quite easy to do. But in general, first of all, we'll set up the problem in the following way. Okay, first of all, I have the first object here of mass m1, and the first object here initially begins at rest. So the initial velocity, termed v1 is equal to 0. Okay, then we have the second cart like so. This is mass m2. This object is also initially at rest. The initial velocity of object number 2 here is equal to 0. And then the objects explode apart. What actually happens during the explosion itself, we'll actually treat that as an individual topic later on. But after the explosion occurs, the first cart here, m1, moves off to the right-hand side with a velocity v1 final of plus 1 meter per second. Okay, now when I write these velocities down, keep in mind that they are velocity vectors, they're not speeds. I wrote down the plus sign there for clarity. Okay, and then we've got the second object, m2. Now presumably, of course, it moves off to the left-hand side. We'll have to show that explicitly, and it does so with an unknown velocity, v2 final. That's the unknown here in parts A and B. Okay, now here's then how we set up our conservation equation. This is just a one-dimensional problem with two particles. So I'm only going to have here two terms, and then I can drop the vectors signs here for this one-dimensional case as we always do. And then all that I have to do is for each individual object is fill in the final value of mv minus the initial value of mv into the various terms. The right-hand side of the expression here is still the change in the momentum of the center of mass of the system, but I actually don't even have to worry about the center of mass itself when we perform the calculation. Here's then what happens. So first of all, object number 1. Its final momentum after the explosion is m1 times v1 final, minus then the initial value, which is equal to 0, because this object begins at rest. So the first term here is m1 v1 final minus 0. And then next we look at the second object, just all by itself. We take its final value of mv minus its initial. So the final value of the momentum of object number 2 is going to be the mass m2 multiplied by the unknown v2 final, minus then the initial, which is also equal to 0, because this object begins at rest. So the second term here is m2 v2 final minus 0, and then equals 0 here on the right-hand side of the expression. And then all that we do is just solve for v2 final. So to solve for v2 final algebraically, I'll just move this term here to the other side. When I do, I pick up a negative sign. This will indicate the direction of the v2 final in just a moment. And then lastly, divide by m2 on both sides. And then therefore, I end up with the following expression. And now I just apply the expression here to the two situations that we have in parts A and B. Now in part A of the problem, it says that we're assuming that the carts are of equal mass. So what we're saying then explicitly is that m1 is equal to m2. If m1 is equal to m2, then they obviously just cancel from the expression, and the final velocity of object number 2 is just the negative of that of object number 1, that's equal to negative 1 meter per second. So basically just think of it this way. Everybody starts off at rest, so the total amount of momentum to begin with, the total amount of mv, is 0. It has to be 0 the whole time because there are no external forces acting here. So then therefore, as they explode apart, if this guy goes off in this direction with momentum mv, this guy here has to go up in the opposite direction with the same amount of mv. So the two, one positive and one negative, just cancel each other out. So if they're of equal mass, then they'll have the same speed, but just in obviously opposite directions. Okay, and then secondly here, part B. Excuse me. given in part B is that one of the carts now, M2 in this case, is twice as massive as the first. Before we set up and solve the problem by using our expression, let's just see if intuitively we can figure out how this has to happen. So then now we're going to be given the following. Here's once again M1. It's still going to explode off that way at 1 meter per second, but now here's M2, which I'm going to say is twice as massive, like so. So then as the explosion occurs and this guy here moves off at 1 meter per second in this direction, what do you suppose this guy's speed is going to be in the opposite direction? It's going to be 1/2 meter per second. Like so, notice how his speed is less than that one. The reason for this, once again, is that the mv here, basically in this direction, 1 times 1, has to cancel out with the mv here, in the opposite direction, 2 times 1/2. We can then show that here explicitly using our expression in the following way. All I'm going to do in the expression is take m2 here in the denominator and replace it with 2m1. So V2 final then ends up being this. Okay, the m1's just cancel each other out, and we're left with negative 1/2 of V1 final, which is equal to negative 1/2 meter per second. Once again, the total mv of the system is equal to 0. It has to be 0 the whole time, so the mv of one cart in one direction cancels exactly out with the mv of the opposite cart in the opposite direction. And now in part C, we're asking the following question. Is it possible for an object, or in this case these two carts, to explode into two pieces in a plane? In other words, why is this truly a one-dimensional explosion? Well, think of it this way. Let's say that my two carts once again explode apart. Let's say that this guy here, by definition, moves off in the positive x direction. Is it possible for this second cart here to explode such that it has like a y component, like this, to its velocity vector? The answer to that is no. Because if this guy moves off in this direction with mv, this guy has to move off in the exact opposite direction with the same amount of mv, such that the total is equal to 0 the whole time. If this guy here exploded off like so, such that it had a y component to its velocity vector, there's nothing about this guy that would cancel it out. In other words, that y component would have been created somehow that violates then the conservation equation. So that's why this is referred to as a one-dimensional explosion. If two pieces explode apart, or an object equivalently explodes into two pieces, the velocity vectors immediately after the explosion are linear, just in opposite directions. That's why it's called one-dimensional.
I understood the description like when you were speaking it, but could you tell me how we got 2m1 to...
Okay, so you just kind of have to read what's there in words and rewrite it as a mathematical statement. It says the second cart, M2, is twice as massive as the first cart, M1. So it took what was written there in words and wrote it as a little mathematical statement, and then boom, we arrive at our answer. So, okay? That's literally all there is to it, to the one-dimensional explosion. The two-dimensional explosion is much the same idea, it's just a little bit more complicated mathematically. Let's take a look at that. Okay, first of all, there's this very wordy description of the explosion itself, which I'll begin to draw out for us on the board in just a few moments. Sean, what was the answer to part C? So the answer to that part C was no. It truly is a one-dimensional explosion because you have mv in one direction canceling out exactly with mv in the opposite direction. You know, there's a very wordy description here for a simple picture. I'll draw that out, of course, for us in just a few minutes. But what we have are three objects crammed together, or equivalently, an object explodes into three pieces. Once again, we'll assume that this all takes place on a horizontal frictionless surface. Let's assume that everybody starts at rest. And then after the explosion, we're given all of the details of the final velocity vectors of the first two pieces. Basically, we want to figure out in just a few moments what's happening with the third piece. Finally, almost done grading the last exam. The last couple of stragglers have taken the exam. I should have the exam scores up on Infinite Campus, certainly by 2:30, 2:45, for better rulers, right? Okay, and then part A, what's being asked for here is the velocity of the third piece. Making the numbers here, by the way, in the problem just really easy to work with. The masses of the objects are just 1, 2, 3 in kilograms, 3 kilograms respectively. The speeds of the first two pieces are just 1 and 2 meters per second. We're given their directions here in the problem as well. And then we just have to find the details of the final velocity of the third piece. All right, so here's the picture that's being described here rather extensively in the problem. So we have our three pieces here like so. Off to the side, M1 is 1 kilogram, M2 is 2 kilograms, and M3 is 3 kilograms. And as it says, all objects begin at rest. And then boom, everybody explodes apart. Now the first piece, it says by definition, goes off in the positive x direction like so. So here's M1 with a speed V1 final that's given to us as 1 meter per second, but it is along the positive x-axis here by definition. Okay, and then the second piece explodes off into the first quadrant at a 45-degree angle. So the second piece does something like this, like so. So here's M2 with its final speed, V2 final equal to 2 meters per second. But with respect to the positive x-axis, this guy here forms angle theta like so. That's equal to 45 degrees. And then we've got our third piece. Just using a little bit of mathematical intuition into which quadrant, first, second, third, or fourth, would you expect the third piece to probably explode into? Third. Probably the third quadrant. It may end up looking something, say, like this. Like so. So right here is M3 with a V3 final. But there's a couple of things, of course, that we don't know about it. We don't know what the magnitude of the V3 final is, nor do we know its direction. So let's think of the direction associated with the unknown V3 final vector as this unknown purple angle phi. Like so. This is the basic diagram here for this two-dimensional explosion. Okay, now immediately our conservation equation here is a little bit more complicated than it was for the previous example, because number one, we have vectors here to worry about. It's a two-dimensional situation. And there's also now three objects here that make up the system. So I'm going to have three terms for my conservation equation, change in momentum of each object added together. The right-hand side of the expression is still the change in the momentum of the center of mass of the system. That's equal to 0 because momentum is a conserved quantity. Okay, now the easiest way to approach this equation, and this is typically how you'll see it done in introductory textbooks such as your own, is that we break the expression up into components. We look to see what happens in the x direction first, and then afterwards we look to see what happens in the y direction. Now in terms of the x direction first, there's a certain notation that you'll see. It's usually depicted in the following way. There's a little subscript x that we use for each individual term here, because we're looking at the change in momentum of each object specifically in the x direction, like so. And then all that we have to do is fill in, once again, final minus initial, and now specifically we're talking about the components in the x direction. So let's take a look at first object number 1. Its final momentum after the explosion, that is in the x direction, is just going to be m1 times v1 final, because remember that object number 1 explodes off into the positive x direction by definition anyway. And then minus the initial momentum of number 1 in the x direction, which is just simply going to be equal to 0. In fact, all of the terms here in the x direction and also later on in the y direction, the initial momentum of each individual object in both of those dimensions is going to be 0 the whole time, because everybody begins at rest. So all of these terms here in both the x and eventually in the y direction, they're all just going to be in terms of minus 0. Like so. Now we get the object number 2. Once again, this is so far in the x direction. So to find the final momentum of number 2 in the x direction, I have to take the mass m2 and then multiply it by the x component here of v2 final. That's going to be v2 final times the cosine of the angle theta. Because the v2 final vector by itself, remember, of course, looks something like this. Where here are our components, and then right here is the angle theta. Right here, the adjacent side of the triangle, of course, is v2 final cosine theta. So the final momentum first of object number 2 here in the x direction is this. And then once again, minus 0, the initial momentum, because everybody begins at rest. Then we get to our unknown, number 3. We have to first of all write down its final momentum in the x direction. Well, that's just going to be m3 multiplied by the x component of v3 final. Don't make any assumptions about positive signs or negative signs associated with the components of this vector. That will come out in the solution itself. Now the v3 final vector here off to the side looks perhaps, we don't know as of yet, something like this, where its components are here and here, and then here with respect to the positive x-axis is our unknown angle phi. So the x component here of the v3 final vector, this guy right here, is still just v3 final times cosine of phi. Don't make any assumptions about positive signs or negative signs. That comes out in the answer in just a few minutes anyway. So the final momentum of number 3 in the x direction is the mass m3 multiplied by that x component, minus then the initial value, which is once again equal to 0. Everybody begins at rest. So now what do I solve for here? Do I solve for v3 final? Do I solve for cosine phi? No. What you actually solve for is the whole thing. You solve for v3 final cosine phi, because when you solve for that quantity, you're solving for the x component here of the v3 final vector. And then in just a few moments, we repeat the process in the y direction. All the cosines that you see here will just turn into sines, and then we solve for the y component here of the v3 final vector. That's the basic idea. So we solve for this guy here first. So at this point, you just have to do the algebra. So I take these two terms, here and here, I'll move them to the right-hand side. They'll both become negative, be careful as we do. And then we divide by m3 on both sides to get v3 final cosine phi by itself. So punching through the math, move these guys over to the right first. Both become negative, like so. And then I just divide by m3 here on both sides. And now I plug in my values. Now, if v3 final is in the third quadrant as I'm guessing, this should work out to be a negative number. It's pretty obvious that it does. Okay, now we get to the numbers themselves, and all this is done in degree mode on our calculator, by the way. And now we just have the following. Negative 1 times 1, this is why I made the numbers easy. Negative 1 times 1 minus 2 times 2 times cosine of 45, and then divided by 3. So negative 1 minus 4 times cosine of 45 all over 3. And this comes out to be negative 1.28 meters per second. So that's this component right here. Its magnitude is 1.28 meters per second. Now we just repeat the process here in the y direction. All the cosines that you see here in this expression basically just turn into sines. Incidentally, there is a cosine associated with this m1 v1 final quantity, the final momentum of number 1 in the x direction. It's specifically, however, the cosine of what angle?
0.
Yeah, it's the cosine of 0 because it explodes along the positive x-axis. But technically speaking, there is a cosine. Okay, now, just set this up in the y direction. Once again, initially here, there's a little bit of notation. So we have change in momentum of each one in the y direction now. So we have that subscript like so. 0, right-hand side is still the change in the momentum of the center of mass. And then we just start filling in all of our terms. All of our terms are going to be, once again, just minus 0, because the initial momentum of everybody, remember, is equal to 0. Everybody starts at rest. So for object number 1 first, take a look carefully. What is the final momentum of object number 1 in the y direction?
0.
Yeah, it's equal to 0 by definition, because this guy explodes into the positive x direction. Now, technically, it's m1 v1 final times the sine of 1a, sine of 0, which is equal to 0, but that final momentum of object number 1 in the y direction is equal to 0. You gotta write it like this here in your notes. Okay, then we get to number 2. So its final momentum in the y direction is the mass m2 multiplied by the y component here of v2 final. That's this guy here in the spectral triangle. That's v2 final sine theta. And then minus the initial, which is equal to 0. And then we get to our unknown, object number 3. Once again, we don't make any assumptions about positive signs or negative signs or anything like that. So its final momentum in the y direction will be mass m3 multiplied by the y component of v3 final. Remember, that's this guy right here. This is just v3 final times the sine of phi. You just write it like that. Let the negative signs take care of themselves mathematically. Minus 0, because once again, everybody begins at rest. Yeah, go ahead.
Can you re-explain why it's 0 minus? I didn't get minus 0.
Okay,
Why is the first
so
one?
final momentum of number 1 in the y direction is equal to 0, because by definition, number 1 exploded into the positive x direction. Now you could think of it, however, as m1 v1 final times the sine of 0 degrees, but sine of 0 is 0 anyway. And then the minus 0, once again, for every term, not just y, but x direction as well, is because everybody begins at rest. Okay, now in the expression that we arrived at here, this here is what I then solve for. This is the y component here of v3 final. So to do that, just move this single term here to the other side, and then divide by m3 on both sides to obtain the following. Diego, you all right? Staying with me, all right? Like so. And now just plug in. So minus, and then just 2 times 2 times the sine of 45 over 3. Once again, I kept the numbers here easy for that reason. So negative 4/3 times the sine of 45. This comes out to be negative 0.94 meters per second. Now that being negative, of course, here's its magnitude, by the way. That being negative means that, yeah, the final velocity of object number 3 is obviously into the third quadrant. Now the problem is phrased that it's asking us for a velocity. So leaving it in component form as the answer is perfectly fine. That is v3 final is equal to negative 1.28 I hat from earlier minus 0.94 j hat meters per second, obviously third quadrant. And then lastly here, for this two-dimensional explosion problem, just a couple of other minor details. Let's take a look briefly at an energy calculation. Didn't do this for the one-dimensional problem, but we can do so here. And then lastly, in part C of the example, kind of like in the last part of the previous problem, we'll take a look at, once again, a question involving the basic physics. So how do we get a handle on how much energy is released in the explosion itself? We'll just think of it this way. Let's say I've got 3 objects, like so, and I begin with some form of potential energy, like the potential energy associated with these elastic bands. And then everything explodes apart. These guys go like so, this guy goes like so. So what happened to that potential energy? Well, it just turned into the kinetic energy of the pieces. So the energy that's released in the explosion is just the total amount of kinetic energy of the individual pieces and nothing more. So part B of the problem then we can think of in the following way. The energy released E is just the sum of the kinetic energy of the individual parts. K1 plus K2 plus K3, and we just total that all up and get some number in terms of joules. Now remember, of course, from our last unit, chapters 7 and 8, that kinetic energy is 1/2 mv squared. So the kinetic energy of piece number 1 is 1/2 m1v1 final squared. Number 2, 1/2 m2v2 final squared. And then lastly, number 3, 1/2 m3v3 final squared. And all that we do is just plug in everything and get some joules. Be careful here, nothing cancels out or anything like that. We just plug in and get some number. But also do remember that all of these quantities here are speeds, not velocities. Now I do have the final speeds of objects numbers 1 and 2 after the explosion, but I don't quite have that for the V3 final here. I do have to find the speed by doing a little bit of Pythagorean theorem. That is then what's going to get plugged into this expression here to get the total kinetic energy released. So I do have to do a little bit of Pythagorean theorem here with these components to get that speed V3 final. So that's 1.28 squared plus 0.94 squared, square root all of that. Comes out to be a speed of about 1.59 meters per second. That's the speed that has to get plugged into here to get the total amount of kinetic energy of the particles after the explosion. So lastly, let's see what we get here. 1/2 times 1 times 1 squared, so just a half, plus 1/2 times 2, which cancels, times 2 squared, so plus 4. And then lastly, it's plus a half times 3 kilograms times then 1.59 squared for that final speed of object number 3. This works out to be 8.3 joules. So the energy released in the explosion is just the sum of the kinetic energy of all the parts after the explosion itself. Then lastly, can an object explode into 3 pieces in 3 dimensions? Now here's what I mean by that. Yes, the explosion takes place in this room. This room is obviously 3-dimensional. But what about the velocity vectors after the explosion? Think of it this way. So once again, we have our 3 pieces. Let's say that 2 of the pieces, the carts, by definition, explode into the XY plane, the plane of the desk. Is it then possible for the 3rd piece to explode, say, like so, where it has a Z component here to its final velocity vector? No, and the reason for that is because if these guys just have X and Y components, this guy here must also just have X and Y components, so everything cancels out, like the 1-dimensional problem a little while ago. So when an object explodes into 3 pieces, the reason why we call it a 2-dimensional explosion is because the velocity vectors immediately after the explosion are always coplanar. They only form a plane. The velocity vectors themselves, in other words, don't appear in 3-dimensional space, they only appear in 2-dimensional space. That's why this is called a 2-dimensional explosion. So the answer to this question is no for that reason. So at a minimum then, how many pieces must you have such that when the objects explode apart, that you truly end up with what is called a 3-dimensional explosion? It has to be at least 4. So 4 or more pieces, that's the 3-dimensional explosion. Don't worry, the 3-dimensional explosion is a horrible mathematical mess. It's not necessary for us to take a look at it. Just the 1 and 2-dimensional cases are all that matters. Yes?
Do you do that in AP?
No, not even there. I mean, there's ways to make the geometry simple, but it's at least initially, it looks like a trigonometric nightmare because you have velocity vectors in 3-dimensional space. You have to form Cartesian coordinates in 3-dimensional space. Blah blah blah. Okay, that's explosions. Nothing to it. Let's take a short break.
But was it like using like
Okay, now banging it together, now just press it to begin with, and then next one.
Yeah, it was basically, it's two-dimensional, basically.
How many were there?
1-dimensional case of velocity.
I mean, I know it didn't say like specifically, but you know, it wasn't like those questions.
Velocity.
Questions.
Okay. got this guy going in
Yeah.
this direction, this guy going off in
You
the
should just
direction.
integrate.
They just cancel out, like zero. And like,
Yeah.
let's say
Was there any agreements on
Yeah, there were like two or
so they're in
Oh,
the.
so no, that trapezoid.
This guy will have to go
There's
off
one.
like this.
And then wasn't there one where you just like,
Cancel out.
that's
These
equal
guys
to
will
integral
have
or
to-
two dash, like wasn't that?
So that's why it's a two-dimensional explosion.
I don't know.
No.
It's like soccer.
I tried to forget that.
And then what else?
Okay, so, if we have the object.
No, it's just straight.
This guy can't go like that, because he would have a Z component. It's not
Oh, yeah, I
connected
can't
to
tell.
these guys.
Don't.
Remember that everything.
Oh, wait, yeah.
So if these guys are in the next one
They
plane,
would
this guy also
take
has
the
to be in the
derivatives
next one
within
plane,
it.
because the sum of everything
Like
is always
within
zero.
zero to x squared.
That's right, you need four more pieces,
Derivatives
that's
with
right.
integral.
It's
Yeah,
just
so
the
you have
original
like
function.
four pieces,
Yeah, but if
one,
it's x
you know,
squared,
these guys go like that, that guy goes up, that guy goes down.
Derivative of the.
Oh yeah, fundamental calculus.
Yeah, you gotta remember that. There's like
Yeah.
one question about it, but like,
Yeah, I remember that.
shoot, which,
Did you remember it?
I think it is, I'm not sure. I forgot like a minor detail, but my answer that I got was.
Oh, yeah, you called my name.
So,
Probably right.
no,
That
it's
was
probably,
your
I
answer.
think I throw me out.
You never know.
We took it do you think Bucky's getting interrelated?
What did I say 10 minutes ago?
I didn't hear you.
But my family calls me like.
What's you wanna?
Thought you were just ignoring me. I couldn't hear what you said.
Where?
No, I was thinking of putting on like and closer to this.
Oh.
Weird.
No, all over there. No, it's not like that. I'll say that it's not.
Oh yeah, that's right, they can trip.
Which other one?
No, I'm just gonna do it.
Yeah, we'll take one of my football clothes from my car. And then we'll drive to your car, and then I'll take my car with your car. There's sort of ours, I'll throw it. Let's go to there.
But I need to.
And then some football games.
I'm going
Those
to.
are the games I have.
Right now?
Wow.
It's
Oh,
cold.
but in the football lot. Was there a game tonight? Who's football? Who's football? Anything here? Is there a football game tonight? What? Is there a football game? Isn't the football season over?
Yeah, the Super Bowl already happened, but it's here.
Well, then why?
Best half of football, by the way, I've seen in 20 years.
You think so?
It's not like a home.
That's very
Oh, the
big.
fight, I love it. I was like, yeah.
Basketball. Oh, baby.
Mr. Shaw, college is way more interesting than this.
No, but it's so
College-
sloppy.
College football is unwatchable.
No, it's
so bad.
It's so
Played
much
so badly. I'd rather
No.
watch Pee Wee League.
No, he's so right.
Because it's all offense.
Exactly, just like college basketball, there's no defense. No one knows how to play
College
defense.
football is the
That's
worst
the dumbest thing I've ever heard. College.
Are you kidding me? I love college football.
No, college
What's wrong
football
with
is definitely
college
awesome.
football?
boring, it's not.
Not good.
You're right.
You kidding
I'd
me?
rather get kicked in the head than watch college.
What's wrong with college football?
I enjoy it.
That's what I'm saying. It's so right.
I'm so disappointed right now.
What is that?
Who's the leading scorer in NHL history?
Wayne
Gordy
Gretzky.
Hawn. Either that or Wayne Gretzky.
Wayne Gretzky.
Yeah, Booz Gretzky. I don't know that much about hockey.
Hit the fucking
385 horsepower.
What's soccer? Kick the ball and chase it.
What's basketball?
So throw the ball and chase it.
What's water polo?
Just
Throw the ball and chase it.
I don't chase it.
Pee in the water and chase it.
That's true, that's true. No, but you have to swim out.
Pee in the water and swim after.
Oh, really?
Oh.
They don't make any sure they can random. They don't make any more. I've got a G before that. My mom's friend said it was the manual, he put a racing.
All right, let me go ahead and move on. As you'll see, when it comes to collisions, quantifying problems associated with it, the process of treating collisions is very similar to that of explosions. But before we do, it turns out that this is actually a good place in the class, once again, for the story to continue. It's been a while since I've told you a story. It was time to get some more of the story. Yes, so it's story time. Okay, collisions, as an experimental procedure, are extremely important in physics.
Is all this not cool stuff like necessary to make
That's important. Okay, the reason I say that is as follows. It turns out that, experimentally speaking, collisions are kind of like the only game in town, if you will, when it comes to trying to discern the nature of matter at the smallest of possible scales. The basic idea is actually quite simple. What we do is we take subatomic particles and we accelerate them to extremely high speeds. We accelerate them to extremely high energies. And then we basically smash the stuff together and we look at all the debris that comes out. The more energetic that you do this, the more finely the detail you can look at the smallest of scales. And when you start to look at nature at the smallest of scales, it's like you're looking at the nature of reality itself. This idea of smashing matter together to discern the nature of reality kind of lacks a certain elegance. It's someone once, for example, compared it to like trying to learn about classical music by taking a piano and throwing it down a flight of stairs. Or like trying to learn how finely made instruments like Swiss watches work, not by like slowly taking them apart and looking at the stuff, but instead smashing them together at really high speed and looking at all the debris that gets sprayed out. So it kind of lacks an elegance in terms of trying to discern how nature works, but it truly is the only game in town. So the reason why, as an experimental procedure, collisions are extremely important is that they are the only means that we know of, only means of exploring the inner constituents of matter at the smallest of scales. So the idea, basically the idea is to smash subatomic particles together at extremely high speeds, at extremely high energies. And examine the debris. At the smallest of scales. Now, the very first experiment of its kind dates back more than a century. And it turns out that everybody here in this room has heard of it. It's what's called the Rutherford gold foil experiment. The Rutherford gold foil experiment, learn about it maybe in chemistry class or, God help you, integrated science, if you recall, is essentially a collision experiment. Here's what's being described. So the first experiment of its kind. Is the famous Rutherford gold foil experiment. Hey, Ernest Rutherford was a New Zealander. He lived in Great Britain at the time. He was at Oxford University, I believe. He performed the experiment in 1911, and it ultimately won him the Nobel Prize. Okay, if you recall some of the basic details of the experiment, it essentially went in the following way. What he did was he took a piece of the newly discovered element uranium. Here's a chunk of it, like so. And uranium, as I previously had mentioned, undergoes the process of radioactive decay. It slowly loses subatomic particles and decays into lighter elements. The process of radioactivity was just being recognized at the time. Over 100 years ago, the process itself was not understood. But even if he didn't understand the physics of the actual process, he realized that he could use the process of probing the inner constituents of atoms. In other words, trying to discern how the atom itself is structured. When uranium naturally undergoes radioactive decay, it emits positively charged particles that have a high amount of energy. In other words, they're moving at a pretty good clip. These positively charged particles at the time were just referred to as alpha particles. We actually still call them that today. But today we do in fact understand the physics of radioactive decay. These alpha particles, it turns out, are actually helium-4 nuclei. 2 protons and 2 neutrons bundled together by means of the strong nuclear force. So these are helium-4 nuclei. And then basically Rutherford said, he said, all right, well, I know that these are positively charged and they're moving pretty fast, even though I don't understand the process of radioactive decay itself, but I can use these guys here if I slam them into a target as a means of probing the inner constituents of matter. And the target itself, of course, is the famous thin gold foil. It truly was thin, by the way. It was only a few hundred atoms thick. And the reason why they chose gold is because gold, even though it's a heavy, dense metal, it's actually very soft, it's very malleable. So it's actually easy to arrange into really thin sheets. And this is capable, we had the capability of doing this even as long as 100 years ago. So here's basically our target. It's the thin gold foil. Now here's the analogy that Rutherford used. It's like taking a high-powered rifle and shooting bullets at tissue paper. So then what would you expect to happen if you did that? The bullets just go right through. So. And that's exactly what happened. However, less than 1% of the time, some sort of collision would occur deep within the atoms of the gold itself. One of these positively charged bullets would like hit the tissue paper and boink, get bounced off in a different direction like so. There would be a collision of some sort. And statistically, in terms of the experiment itself, this happened less than 1% of the time. It's like firing a high-powered rifle at tissue paper, and the bullet every once in a while bounces back and hits you in the face. That's kind of the analogy here to use. Now, how did Rutherford know where all these particles were going? Well, placed around the entire apparatus were a series of screens. One here, say, one here, one here, and so on. Now these screens were coated with a chemical compound called zinc sulfide. When charged particles strike a zinc sulfide screen, there is a little bit of fluorescence. Some of the energy is converted into light. So you can keep track of the particles in this manner. Now let me show you this a little bit. I'm not going to show you the actual experiment itself, but I am going to show you how charged particles, when they strike a zinc sulfide screen, in fact cause the screen itself to fluoresce. This right here is a very primitive version of something called a cathode ray tube. If you want to think of it, it's actually like a very simple primitive ancestor of an old style tube type of television. I'll tell you a little bit about how TV works in just a few minutes. But for now, cathode ray tube is actually quite simple. What you have here on this side of the tube is a metal spike, and then over here on the other side of the tube is another metal spike. And then when I plug this in by means of this device here, this here is an example of something called a transformer. A really high voltage is created between the opposite ends of the tube. In this case, it's actually several tens of thousands of volts. Think of a voltage as like a really steep hill. That hill is so steep that it's actually able to tear electrons out of the negative side of the terminal here. Those electrons then fall across the tube to the positive side, which is over here. However, as the electrons are falling through the tube, some of the electrons strike this intervening screen. I'm facing it towards you, but if you look carefully, notice that the screen kind of looks like a whitish green a little bit, like so. That's the chemical compound zinc sulfide. So when the electrons strike the zinc sulfide, then it fluoresces. So you're not going to see the individual electrons themselves, of course, but you're going to see their effects when I plug this in. This, by the way, is actually a little dangerous because, as I said, the voltage here is in the neighborhood of several tens of thousands of volts. And I actually have some exposed wires here. So you have to be nice and careful, Dave. Nice and careful. So. Okay, so of course, you're not seeing the individual electrons, but you're seeing their effects as they basically fall from one side of the tube to the other. Some of those electrons strike the zinc sulfide screen, which then fluoresces. So that's the basic idea of how, for example, Rutherford was able to keep track of where the particles were going in his experiment by placing these detectors, if you will, these screens kind of scattered around the apparatus. So he knows where the particles are going. Now, how this relates to TV, I'll get to in a little while. Okay, now, the mathematical details of the collision here, when Rutherford analyzed his data, led him immediately to three conclusions. So, three conclusions from the collisions themselves. The first, very simply, is that the overall volume of the atom is mostly empty space. The reason why we know that is because most of these positively charged alpha particles would go right through the gold foil as if there's nothing even there. So when we say that the atom is mostly empty space, our first experimental piece of evidence that supports this idea is this portion of the Rutherford experiment. So because most of these guys just go right through, the atom is mostly empty space. Okay, and then second, whatever the target was here that was being struck by this positively charged alpha particle, well, it also has to be positively charged, because remember that like charges repel. So the target is positively charged. And then thirdly, the target has to be very massive. Now, when I say massive, I mean massive in the sense that it's basically the entire mass of the atom itself. The reason why is because in some of the cases regarding the collisions, the alpha particles would actually get kicked back in their original direction of motion, like so. It's like hitting a wall. It's like throwing a tennis ball against the wall, and it bounces right back at you. So then, therefore, compared to the overall mass of the atom itself, the target itself is extremely massive. Hey, pretty obviously, what am I describing the discovery of with these results? That is about atomic structure.
Nucleus?
Yes, this is the discovery of the atomic nucleus, obviously. Okay, the results of the experiment won Rutherford the Nobel Prize, but perhaps even a little bit more importantly, he kind of like hits upon the answer. Experimentally, how do we go about exploring the inner constituents of matter? You basically perform collision experiments. You basically smash stuff together. Let me show you some slides now. Once again, it's still story time, right?
Yeah.
Once upon a time, there was a New Zealander running around somewhere in England. There he is. There's Rutherford. Okay, so he performed the experiment in 1911, and in doing so, Rutherford discovers that collisions provide the best means of probing the inner constituents of matter. And then we get to the pre-World War II years. And by the way, his apparatus itself was actually quite simple. It was all done on a pretty small scale at low energies. It all basically just took place on a lab table. It could easily fit on my desk. And the basic layout here, essentially what I drew on the board, is depicted here on the slide. What he actually did was he took the piece of uranium, the source of the alpha particles themselves, and he put them inside a lead box. Okay, lead is a very dense, heavy metal. It doesn't let the alpha particles through it. But on the side of the box over here, tilted away from us, there's a little hole. So then therefore you have the particles emerge from that hole in a nice tight beam. You then take that beam of particles, have them slam into a target, collisions occur, and then right here you have your detector going all the way around the apparatus. And then the mathematical details of the collisions themselves, just depicted here with this simple diagram, ultimately led to our understanding of the atomic nucleus. And then, as I said, we get to the pre-World War II years. Here, let me do some erasing. Take a moment there to read the slide. Once again, still kind of taking place on a small scale, the experiments that followed Ernest Rutherford's famous experiment led to our understanding of the atomic nucleus. It's through these experiments, up in the decades leading up until the Second World War, that, yeah, we know that the atom's nucleus is composed of two small particles, protons and neutrons. We learned that the basic layout of the periodic table. Remember how the periodic table is structured. In other words, what makes an element an element? That's the atomic number. The atomic number, if you recall, is the same as the number of protons that make up the nucleus. That's what determines what the element is. So the periodic table, by the way, was discovered by Mendeleev and a few other chemists in the late 19th century, essentially the 1870s or so. But it was physicists in the 20th century that understood why the periodic table is laid out the way it is. And it has to do with the structure of the atomic nucleus, which then determines how the electrons are arranged around the nucleus. Remember, for example, that the atomic number, the number of protons, is also the same as the number of electrons, because the positive charge of the protons exactly cancels out the negative charge of the electrons for neutrally charged matter. So all of the gory details of the periodic table that you learned, for example, in chemistry class, all of that was basically worked out in terms of atomic nuclei by collision experiments in the decades leading up into the Second World War. So there's a nice little saying or a nice little story that physicists like to say. Basically, chemists, yeah, they discovered the periodic table experimentally back in the 1870s, but it was physicists who derived it in the early 20th century by doing collision experiments. So, as the experiments proceeded, after Rutherford, they still took place on a small scale. But led to our understanding of atomic nuclei and the basic layout of the periodic table. Once again, however, as this was all going on for a couple of decades prior to the Second World War, it was all being done on a small scale at relatively low energies. Okay, now before we get to the Second World War, which is actually very key in the history of physics, I can get to briefly here. This gentleman. This is an American physicist named Edwin Lawrence. And Edwin Lawrence, by the way, is who the Lawrence Livermore National Laboratory up near Berkeley, for example, is named after. He's a very important figure here in the history, if you will, of particle physics, because he invents one of the very first accelerators. An accelerator is basically a device that accelerates charged particles up to extremely high speeds, up to extremely high energies. His device, the first one of which actually fit here in the palm of his hand, is what's called a cyclotron.
The type of transformer.
No, it's not a type of transformer. No, it's not a city in Star Wars or anything like that. A cyclotron is a type of particle accelerator. way that it works is as follows. You basically have a circular track, and you then line the circular track with magnets. Because magnets, and I'll show you this in just a moment, magnets exert forces on charged particles. So you can then accelerate the particles to extremely high speeds, extremely high energies. If you do this along a circular track, you can have the particles then go faster and faster and faster and faster, and then you can redirect them off to the side, for example, and slam into a stationary target. Or you could have another beam of particles moving in the opposite direction. You could have a beam of particles moving in this direction that are positively charged, a beam of particles moving in the opposite direction that are negatively charged, and then you can direct the beams into each other like so, such that you can then cause a collision to occur at extremely high energies. So a cyclotron, this type of circular particle accelerator, is lined with magnets. It's a circular track, if you will. Magnets exert forces on charged particles. And I'll show you that here in just a moment. Somebody had a hand up. William? Or, I'm sorry, John.
I was reading something a few weeks ago, how they have particle accelerators that are.
Yeah, I'm gonna show you pictures of the big ones in just a little while, but yeah.
Or are they using them to like sort of design artificial black holes by like drones?
Yeah, I'll show you that in just a little while, yeah. You're anticipating some of the stuff I'm gonna mention a little bit later on. Okay, before we get to the actual accelerators themselves and so on, let me just demonstrate this for you here right quickly. It's very easy to do, how magnets do in fact exert forces on charged particles. So briefly here, I once again set up my CRT like this. And then before I turn it on, right over here, this is a really strong magnet. It's not made of iron. It's made of a very dense, heavy metal called neodymium. Neodymium is a rare earth element. It's very high up on the periodic table. It has a very strong magnetic field associated. It's very heavy. This is much heavier than a chunk of iron. Now watch what happens if I take the magnet, for example, and bring it near my beam of electrons. So, notice that I'm able to very easily exert a force here on the beam of electrons because magnets exert forces on charged particles. Now, how does this relate to old-style tube type of televisions? Well, the reason why they are nicknamed tube is because inside the old-style TVs are multiple cathode ray tubes, each one with a beam of electrons. And then what you do is you use multiple magnets and also electric circuits, which does the same thing, to exert forces on the beams of electrons, and you then have the beams of electrons strike a screen, which then of course forms a picture. More or less through different physical processes, LCDs and modern plasma televisions today do the same thing, basically redirect electrons around to form a picture. But the easiest way of doing this, as it was first discovered in the 20th century, is with multiple cathode ray tubes. First TVs were invented sometime in the early 1940s, late 1930s I believe it was. So think of this right here as a very primitive ancestor of that type of a television. Okay, now why the advantage, or why the bother, if you will, in accelerating particles like so to increasingly higher and higher energies? Well, basically the faster and faster that you smash stuff together, the smaller and smaller pieces come out in the debris, if you will. So you can start to probe the constituents of matter then at the smaller and smaller scales. So this idea of doing this was essentially perfected, if you will, by the invention of the cyclotron by Lawrence, and as you can see here, the first one fit in the palm of his hand. Then we get to the Second World War. The Allies won the Second World War because of two inventions that came from pure physics research. The first of those inventions was radar. Radar is what enabled the British to win the Battle of Britain in 1942, very early in the history of the war. The reason why radar was so crucial to the Allied victory was as follows. After the Nazis had conquered Poland and most of France, they basically set their sights on the last country, and that was basically England. Prior to invading England, what the Nazis did with their planes is they basically softened everybody up. they carpet bombed the English cities by periodically sending their bombers over the English Channel. The reason why the British were able to repel the Nazis' attacks is because they knew the planes were coming by using radar. They can then prep their defenses. If they weren't able to use radar and detect the planes before they got across the channel, then the Nazis might have been able to soften the English up to the point where the Nazis could have invaded England. If the Nazis conquered England, the outcome of the war would have been much different than it actually was. It's quite conceivable the Allies probably would have lost the war if the Nazis were able to conquer England. So therefore, instead of sitting here in this room and speaking English, we may all have been speaking German instead. Basically, the British were able to repel the Nazis because of the invention of radar. And then secondly, of course, at the very end of the war, what enabled the United States to finish off Japan? And that was obviously atomic weapons. Okay, atomic weapons, that technology, of course, is not possible without our knowledge of the atomic nucleus and the strong nuclear force. So all of those experiments that I described previous to the Second World War, leading to our understanding of the atomic nucleus, of course what came directly out of that was our application of atomic weapons. So basically the Allies won the war because of two inventions that came out of pure physics research. Yes?
What about the, from Imitation Game, the decoder?
The which?
Decode, the machine that decoded.
Oh, the Enigma machine?
Yeah.
I mean, certainly there were other parts of the history that were vitally important, you know, key decisions made in the military manner, et cetera, et cetera. But when it comes to the technology that came out of the Second World War, as horrible an event for humanity it was, the benefits of it we're actually still reaping today. Because it actually led to a huge increase in the amount of investment that we put into pure scientific research, and then of course all the technology that comes with that. So as bad as the war was, it actually really was a pivotal event in human history because it really started to push a lot of things forward. And as you can see, these two key inventions were really instrumental in winning the war for the Allies. Now, did the Germans, by the way, also have their own atomic weapons program? Absolutely. You guys know who the guy was who was in charge of the German program? That's right, it's that guy there. It's Werner Heisenberg. Werner Heisenberg was very instrumental in the early development of something that I'm going to talk about in just a few minutes, what is called the Standard Model of Particle Physics. The basic physics of that starts with an aspect of physics called quantum mechanics. He was one of the key figures, along with Niels Bohr, Albert Einstein, and a few other people, that was instrumental in our development of our understanding of atomic structure and how electrons are laid out and so on and so forth. When Hitler was elected Chancellor of Germany in 1933, basically Europe's physicists got the hell out. They went to either the United States, Albert Einstein did. He basically moved to Princeton, New Jersey in 1933 and spent the rest of his life there, or they went to England. And then of course the Second World War starts and everybody starts actively working on their weapons program. Who was placed in charge of the Nazis' atomic bomb program? It was Werner Heisenberg. Werner Heisenberg was a native German. He was conscripted by the Nazis into running their program. He purposefully sabotaged it. He knew full well what everybody else was doing. I mean, he was friends with them. He was friends with Niels Bohr, Albert Einstein. He knew exactly what they were doing. They were developing the Allies' atomic bomb program on the side. So then therefore, what did he do? He sabotaged his own program. At key points in the development of the Nazis' attempt at an atomic bomb, he basically slowed the process down to the point where the Allies were able to get there first, and then ultimately then Germany lost the war. So this is a nice little side point here to the history, once again, in terms of how important these key physicists were in the overall history of the Second World War. But what you kind of take out of this is that the Allies basically won the war due to two inventions that came out of physics research. And it was radar and atomic weapons. Now, atomic weapons were not used, of course, in Europe. The Nazis were defeated prior to their use in Japan. But if the United States did not use atomic weapons to defeat Japan, plans for the United States to invade the Japanese home islands in the spring of 1946, it probably would have resulted in millions of casualties. So as horrible as the atomic bombing may have been at the end of the Second World War, it probably prevented a great deal more mass death that would have occurred later on, because the Allies had plans to invade Japan prior to the summer of 1946 and the spring of that year. But essentially the Allies won the war because of these two inventions that came out of pure physics research. So after the Second World War, the Allied countries, including the Soviet Union, everybody started to dump a huge amount of money and resources into scientific research. In the United States, for example, this is when we started to have the Department of Energy. This is when the National Science Foundation was started. Ultimately, NASA got started a few years later, and so on. So after the war, the Allied countries invested huge sums of money and resources into pure physics research for the obvious strategic advantages.
Cold War have anything to do with that?
Oh, absolutely. The Cold War, in part, was a competition of this investment. One of the reasons why the Soviet Union lost the Cold War is their economy could not keep up with what was required to invest in propelling everything forward. They basically faltered. They fell behind starting about the mid-1960s. And ultimately, economically, this is one of the reasons why the Soviet Union collapsed. So after the war, the Allied countries invested huge sums of money and resources into scientific research. Now you guys are going to be able to start to vote in a year or two. When you start voting, if you ever see any politician that says that they want to decrease funding for pure scientific research, you immediately vote that guy out of office for no other reason. Because of the obvious strategic advantage, the enormous strategic advantage that pure scientific research gives a country. So if someone comes along and they say they want to cut this and cut that with regards to scientific funding, immediately come out of it. So then what happens after the Second World War? Well, all of the experiments that I described previously that took place on a small scale, they now get dramatically ramped up in scale. So for example, compare the cyclotron here that Lawrence is holding in his hand to this cyclotron here. Okay, this cyclotron, which actually, by the way, no longer exists, was called the Bevatron. The BeV stands for billions of electron volts. The standard metric SI unit of energy at small scales is not the joule. Instead, we use something called an electron volt. This machine accelerated charged particles up to energies approaching billions of electron volts. Now, the actual circular accelerator is obviously here, housed in this building. As I said, the accelerator actually no longer exists. It's been dismantled. And what you see here with these gray slabs right here are the rare earth magnets, accelerating the charged particles up to greater and greater speed. Now, what is the advantage of making these machines bigger and bigger and bigger? I mean, after all, aren't we supposed to be looking at stuff that's smaller and smaller and smaller? Well, here's a nice way of thinking of it. Compare these accelerators, as they're called, to telescopes. You want to make your telescope as big as you possibly can. The reason why is because when the mirror is wider, the more light you can collect. So the more light you can collect, the further out in space, and then therefore the further back in time you can look, and the more detail you are able to resolve. Accelerators kind of work the same way. The bigger you make them, the faster you could accelerate the stuff up to higher and higher energies, the more energetic the collisions themselves, the more fine detail you can begin to see. So it seems somewhat of a misnomer. We build these gigantic, most complicated machines that have ever been built to explore the nature of reality at the smallest of scales. The reason why we do is because we're trying to reach energies that literally haven't been seen in the universe itself since almost right at the moment of the Big Bang itself. Okay, now, the Bevatron itself was housed in Berkeley, California. It was actually on the campus of the University of California. It was built just after the Second World War. It was basically running between the 1940s and the 1970s. It was very important in the development of something called the Standard Model of Particle Physics. How many of you have ever heard of something called the Standard Model of Particle Physics? One or two of you. What the hell is that? Take a moment here to read the slide. Now, throughout this course, I've been giving you a basic history of physics, but everything that I talked about in this course took place hundreds of years ago. Where is physics now? Physics today. Physics today, here in the early 21st century, is basically two things. The first thing is Einstein's contribution, what is called the theory of general relativity. I'll give you an understanding at the end of the year of what the theory of general relativity is. Basically what it is, it's our current understanding of the force of gravity. General relativity perfectly explains the universe on the largest of scales. It perfectly explains, for example, what happens as galaxies rotate. It perfectly explains what happens as planets orbit the sun. It perfectly explains what happens, for example, as the universe expands. It is our most beautiful theory that we have as our current understanding of gravity. But then, as a partner, if you will, we have our basic understanding of the other three forces that exist in nature. That's what's called the Standard Model of Particle Physics. The Standard Model of Particle Physics is basically what has emerged from the results of all of these collider experiments that have been done since the 1940s up until about the 1990s or so. Basically what the Standard Model is, it's a complete mathematical explanation of the three other forces that exist in nature. Electromagnetism, and the two types of nuclear forces. The strong nuclear force, that's the force that binds protons and neutrons together in atomic nuclei, and what's called the weak nuclear force. The weak nuclear force is actually what governs radioactive decay. It's another fundamental force that occurs within the atom's nucleus itself. So the Standard Model of Particle Physics is our current understanding of those three forces. It's our current understanding of electromagnetism, which is called E&M, and the strong and weak nuclear forces. The Standard Model of Particle Physics completely explains these three forces. It is one of the most successful theories that we have in nature. It completely describes anything that has to do with those three forces. Our modern technological society, all this junk, all this crap, trivia crap, and all the rest of it, our modern technological society is not possible without the Standard Model of Particle Physics, because this is an application of it. Now, the Standard Model of Particle Physics, as you'll see it depicted here on a slide such as this, basically what this is, and I'm trying to reduce something that's horribly complicated into something that's relatively simple, is it takes all the subatomic particles that come out in these collider experiments and it finds relationships between them. The relationships break the particles themselves into three categories. And how these particles then interact with each other, that's basically then what we see as the forces of nature. Electromagnetism, the strong nuclear force, and the weak nuclear force. These two theories, general relativity and the Standard Model, as I said, is basically where physics is today, and each of these theories is extremely successful in its realm of nature. General relativity passes every experimental test we can conceive of. The Standard Model of Particle Physics passes every experimental test that we can conceive of.